Today, you're going to learn something called implicit differentiation. See, so far what we've done is worked with explicit forms of equations. Let me give you an example. This right here, when you have y equals a function in terms of x, where you have one y, it's solved for, equals some function in x, such as y equals 3x plus 4, is considered or maybe even 3x squared plus 4, is an explicit form of a function. Explicit means y is over here, your x's are over here. You can solve for y. Does that make sense for you?
Yep.
This is explicit. Means y is given explicitly. It tells you exactly what y is. On the other hand, is this an explicit function? Is y solved for itself and then x is on the other side? No, as a matter of fact, you see y is mixed in with x's. This is called implicit form. Implicit means, yes, there's a y there, and you're going to say that y is a function of x, but it's not written as y equals. So y is still a function of x, it's just bound up in the problem. That's what implicit means. So this is implicit. Now, the interesting thing is some of the times, we can make an implicit function into an explicit. Let me show you how in this example. Firstly, if we wanted to solve this for y, I would probably factor out the y and get 1 plus x equals x. Are you with me on that? And if I divide by 1 plus x, I get y equals x over 1 plus x, and that's now explicitly written. So sometimes I can change from implicit to explicit. So if the y is alone on one side, that means it's written explicitly. So explicit y alone on one side. How about this one? Let's see if you kind of get the idea. Would you say this is implicit or explicit? Implicit, explicit.
Implicit.
Explicit would have y equals. Implicit would have y's and x's all mixed up. What's this one? Definitely. Could you solve it for y? Okay, let's try. We solve for y. We're going to get y squared equals 4 minus x squared. And how would you get y by itself? So y would equal the square root of 4 minus x squared. True or false? Think carefully. True or false? What's wrong? Very good, because when you take a square root, you have to put the plus and minus, right? So here's what this says. Well, actually, what is this? Do you recognize the square root of 4 minus x squared and the negative square root of 4 minus x squared? What are those? Difference of squares? No, what I mean, what shape on the graph is that? What's this?
Circle.
That's a half circle.
Oh, yeah.
This is a lower half circle. Do you see this? This is our upper, that's a circle, by the way, radius of 2, centered at 0, 0. So this is an upper half circle and a lower half circle. What that means is that implicit functions can often define two different functions. Implicit equations can often define two different functions. This is not a function by itself, because when I plug in one number, I get out two answers. That says it's not a function. It's an implicit equation. It's actually two distinct functions, an upper and a lower half circle. Do you see what I'm talking about? So oftentimes that's what happens. Implicit equations can define more than one function of x. Just like I did here, this is implicit. That's two different functions. So far we know what explicit means, I hope. We know what implicit means, I hope. That means bound up within that. Y is still a function of x. Sometimes we can solve for it and change it from implicit to explicit. And sometimes the implicit equation will make more than one function of x. Now, consider this example. How about this? Would you say implicit or explicit? What do you think?
Implicit.
Super implicit. Well, that's another level. Super implicit. It's like super whoa. You agree that is implicit, right? Okay, good.
I
You
move
understand.
negative 3y over to the other side and then factor out a y. Divide.
And that. Could you solve it for y? Could you solve it for y in such a way that it's y by itself equals a function
Y by itself. Let's see. No, probably not.
completely an x with no other x's? I mean, sure, you could divide by 9x, but that's still a y. Let me refresh your memory what explicit means. Explicit means there's one y. It's alone on one side, everything else is x's. Can you do that here?
Yeah.
Well, try it. Try it if you want. Can you do it easily? Let me ask you another question. Can you do it easily here? No. No, you can't, because the way you might do this is subtract this over, right? But then you'd have 3y cubed minus 9xy. You'd factor out a y, but you're still left with y squared in there, right? There's really no good way to get rid of that, at least not easily. So can you easily get this into an an explicit form? Can you do it?
No.
The answer is no. This cannot be written explicitly. If there is a way, it's not going to be easy. Sometimes there is no way. You can't write it explicitly for some equations. Now, keep in mind what we're doing here. We're not doing basic algebra, we're doing calculus. And calculus involves derivatives, right?
Yes.
Right. Okay.
Hopefully.
No, we've been doing nothing this whole time. Derivatives. So here's the deal. If this is implicit and I can solve for explicit, I could take the derivative of that. And in fact, that would involve a quotient rule, right? And this one, I could actually take the derivative of the top function or the bottom function and be just fine. That would involve the chain rule or the general power rule because of that 1/2. This one, though, there's actually no way that we're going to be able to get that as y equals something in terms of x. You with me? What that means is, even if you got y by itself, there's still going to be other y's in here that are going to mess you up. We don't want that. So we have to have another method to find derivatives instead of just having y equals a function in x. There's got to be a different way, and there is. And it's called implicit differentiation. That's what we're doing today. So we're going to talk about how we take a derivative of this thing without having to solve it for y. Now that's kind of an interesting question, right? Can you take a derivative without having it y equals? Yeah, you can. We're going to look at that today. So, for example, it's not, the calculus isn't hard. The algebra might be a little bit, but the calculus is not hard. Implicit, explicit. Everybody, what is that? Explicit would be y equals something. Is that the case? This is explicit. This is implicit. This is implicit, this is implicit. Unless it says y equals, then it's not explicit. What is this one again? Implicit. Definitely implicit. Now, we could actually solve this one for y. Do you see that? We'd subtract x cubed, we'd take a cube root, it would be just fine. You could find the derivative that way. But what I'm trying to show you today is how to do this without having to do that, by just solving this derivative, or solving for the derivative without having to solve for y. Because of examples like that, which we're going to have to do that. So we could solve for y, take derivative, or we could use implicit differentiation. Here's the whole deal, though. In order to do this, you must treat y as a function of x. Because if you could solve it for y, y would equal something in terms of x, right? So you have to treat it, and that's going to be important here in just a second. You're going to see why in a bit. You must treat y as a function of x. Must treat y as a function of x. You know how you can add something to two sides of an equation? You subtract something from both sides of the equation, multiply, divide, take exponent, take a root. Pretty much do almost anything you want to both sides of an equation, as long as you do it to both sides. You know that, right? Did you know you can also take a derivative of both sides of an equation? Did you?
I guess
You do
not.
now? You can do anything to an equation that you want to, pretty much, along with taking a derivative. You can do that. So I could actually take a derivative with respect to my variable. What's my variable that I'm dealing with here?
Why?
There's two variables. So how do you tell which one? We're talking about y as a function of x, right? So you're going to have this with respect to x. So we're still treating x as our variable. Y is a function of that variable that you just don't know explicitly. You don't know exactly what it is. Do you get the idea? So y equals something. Right? We don't know exactly what it is because we don't want to solve for it. We don't really care that much. Like this one, you don't really care that much. You're just saying, okay, I know y is a function in terms of x, and that's what we're dealing with here. So we're going to take a derivative of x cubed plus y cubed, and that equals, what do you think, 5 or the derivative of 5? Derivative of both sides. So we treat y as a function of x that we simply just don't know. We don't know what y actually equals, and we don't really care. Here's our steps then. I've shown you the first one. The first one is you're going to take a derivative, or differentiate both sides, with respect to x. Just make sure you do it to both sides. It's an equation after all. You have to do that. So derive both sides. Not signs. Both sides. With respect to x. I'll start you off with the easy side. The easy side is the 5 side. Let's start with the 5 side. Can you tell me what's the derivative of 5, which is a constant?
0.
Very good. If you leave it at 5, you see that would really affect your problem. That would be a problem. 0. Now, let's look in here. Can we take the derivative of these pieces? They're added together, which means I can take them term by term. You with me on this? I'm glad you're here today. This is something you really need to see. Now, the derivative of x cubed is pretty easy to do. We're taking a derivative with respect to x. You follow me on that? In fact, if I wanted to, since that's separable by addition, I could do, I'm going to show this to you one time. We typically won't do this, but I'm going to show it to you here. You could write x cubed, derivative of x cubed plus the derivative d dx of y cubed. Okay with that so far, right?
Yup.
Yes, no? What's the derivative of x cubed with respect to x? How much is that?
3x squared.
3x squared. Very good. Plus. Now, this is the weird one. What's our variable that we're taking the derivative with respect to?
X.
We're taking with respect to, it says right
But
here.
it's a
what
y.
is that? But that's a y. Now here's the idea. Y is a function in terms of x, right? So basically, this is interesting. I hope you find this interesting. I'll show this to you in a second. What you have here is actually a general power rule. You actually have that. Do you see it? It really is this. It's really that. It'd be the same thing, check this out, it'd be the same
Oh.
thing as doing this. 3x squared minus 1 to the 4th. Is this a function of
Yeah.
x? Yes, it's being raised to some power, right? And how you do this is actually with the chain rule, the special version of the corollary, which is called the general power rule. Are you with me on this? You bring down the 4. Watch carefully, I'm going to draw an analogy right here. You bring down the 4, if you found the derivative. You'd have what now?
Squared.
2/3.
Third. Yeah.
You agree with this? But then you don't end there, do you?
Oh, yeah. Of the inside.
Oh, I made it.
Wait a minute, if you did that with this one, you get 3y cubed, right?
That wasn't the evil look yet. Just wait. Have good ones. Losing my train of thought, so easy. We bring it down because that's a general power. We'll bring down the exponent, we subtract 1 from it. Derivative of the inside, you're familiar with this, right? You did homework on that, I hope. If you didn't, well, here's what you were supposed to do. No, that's it, and you would get whatever the derivative is of that, and you would go 6x for that derivative, right? Now, look at the comparison. This is a function in terms of x, that was a function in terms of x. This is raised to some power, that was raised to some power. So the derivative of this says this. It says, sure, you bring down that exponent and you subtract 1 from it. This is no different than what you've been doing. This is actually this right here. Are you with me? The problem is this. In
Actually,
this case, you had to
if it's the derivative of that, it'd be 1. So 1 times 3y squared is 3y squared, yeah.
multiply by the derivative of the inside here. Do you see what I'm talking about? What's the derivative of, what's the inside here? The y. So we multiply by d dx of y. Are you clear on that? Do you see the chain rule at work? Do you see that? You need to see this before you go any further. Raise your hand if you feel okay on getting that part of it. You see where that's coming from? Now here's the weird thing. D dx of y, that says this. Check it out. That says the derivative of y with respect to x. Does it not? The derivative of y with respect to x.
Oh. Oh, that is, okay.
Not? The derivative of y with respect to x.
That's weird.
This says the derivative of y with respect to x, but then so does this. The derivative of y with respect to x. Doesn't that say the same thing here? What does this represent?
It does.
That represents your derivative. You don't get it, do you?
No, the whole thing is.
No, this is your derivative. You get this, that's the derivative of your y. Every time you take a derivative of y, you're going to get a dy dx. Because every time you take a derivative of y, you actually have a chain rule. Every time you have a chain rule, you take a derivative of the inside of it. Does that make sense to you? So every time you're going to have a d dx of y.
So it's derivative of y.
This is the derivative of y with respect to x, right? This is the derivative of y with respect to
That's
x.
so dumb.
That is your derivative. Actually, if you think about it like variables, it's kind of weird, but d dx times y over 1, dy over dx. I don't know if that really works, but I just made it up. You get dy dx. That's what these two things mean. They're equivalent statements. Equals 0. Raise your hand if you feel okay getting down that far. So here's the whole thing for you. You take a derivative of both sides with respect to x. Since you're treating y as a function of x, every time you take a derivative of y, every time, you must get a dy dx. That's really the only important note for today. Everything else works the same. So each time you take a derivative, every time you derive y, you should have dy dx on account of the chain rule. Each time you derive y, you must get a dy dx on account of chain rule. Now, some people might be asking, well, Mr. Leonard, why don't we have a one for this? Why don't we have to use a chain rule here? Well, think about it. Just think for a second. If we did the same thing, you would do chain rule, and you would get d dx of x, right?
It's with respect to x.
If you did the same thing, that's dx over dx. How much is dx over dx? 1. Doesn't matter, right? That's why we don't have to do that. So for our dy dx, though, that is different. This is not the same variable as y. This is a function in terms of x, which means you need the dy dx there. And that's the whole crux of the implicit differentiation. Now, the only issue is this stands for our derivative. This whole thing is all mixed up together. Can you solve for this? This was the calculus, the algebra is the rest of it. Get this by itself, and then you have your first derivative. Okay?
Can you just subtract the 3x squared over divide by 3y squared?
Subtract
That whole.
this,
What?
not this, this.
Yeah. So you keep the y, the 3y squared on that side as well.
Well, for right now, because it's being multiplied.
Yeah.
So
That's right.
subtract,
Yeah.
now we divide.
Okay.
So now that's gone. If we do just a little bit of simplification, we get dy dx equals, looks like negative x squared over y squared to me.
Slope of a curve at a point.
Can you make it down that far? That's our derivative. And notice how our derivative is also implicit. Our function was implicit, so that makes sense. Our derivative most of the times will be implicit as well. Now, could you have done this and got the same exact answer? The answer is yeah, but check this out. Check this out. If you did this explicitly, so if you solved this for y, which is that, if you take the derivative of this thing, are you going to get exactly this? No, because this won't have y's in it, this will. However, you can make a substitution. How much is y equal to?
Negative
That. You can actually substitute that in. That will be the derivative there. Isn't that kind of interesting? Isn't that kind of cool?
Wait, what?
Which is that. If you take the derivative of this thing, are you going to get exactly this? No, because this won't have y's in it, this will. However, you can make a substitution. How much is y equal
okay.
to? That. You can actually substitute that in. That will be the derivative there. Isn't that kind of interesting?
Let me try that. General power rule, third in front, negative a third. This one on goes on top. 3 on the bottom. This is yeah, that goes away. Yeah, that's what you get. Wait, but it's not squared. Wouldn't this whole thing have to be squared? Let's see. General power rule. Or this is 1/3. This is what I want. Use photomath. This should be squared. Let's see how. It's 2/3. That's where I got it wrong. Yeah, okay.
Isn't that kind of cool? Do you see what I'm talking about? Did it go over your head right now? Hope not. Last part. Notice how if I were to solve that for y equals this, right?
Set that down.
Y is here, so this would be that you can do, which is the derivative. If you do this derivative, try it on your own. See if I'm right. Pretty sure I am. But see if I am right. See if you can derive that.
Cube root.
And yeah, it's cube root.
Down there.
It's cube root. Do that. Get to the negative 3/2 power. Oh, sorry, negative 2/3 power. That's going to be right here for you. You're going to have your x squared. You see the x squared in there, right? The 3's are going to be gone because you have a 3x squared, negative 3x squared. You have an over 1/3. You're going to cross those out. You'll have a negative. There's your negative. You'll have an x squared. There's your x squared. You have this thing showing up again to a weird power. It is the same derivative. All right? It's just this one is not explicitly written. This one is. With this function, you couldn't do this. So you won't be able to do this with your derivative in most cases because you can't solve for y. So that's the beauty of implicit, is that this is just as valid as that is. Just as valid. So we do this, step 1, I guess there's only one step. Oh wait, step 2, solve for dy dx. So write a step 2 on your paper somewhere. Step 2 is solve for dy dx. Step 2 is solve dy dx. Okay, guess what? That's it. That's implicit differentiation. If you have this idea down, you have implicit differentiation down. Now, is it going to get tougher? Of course. Yeah, because we're going to incorporate things like chain rule, things like the product rule, things like quotient rule, which you can all do. It makes the algebra nasty. The calculus is not hard. The algebra is, yes, difficult in some cases. Would you like to try some examples to see this?
Yes.
Thought you would. Okay, let's take a look at just a few of them. First one I want to start off with is this one. I say find dy dx. So if we want to find dy dx, that means, of course, we're implicit right here. There's no way we're solving that for y. Oh my gosh, could you imagine? Solve that for y? Not a chance. So we're not going to solve that for y. That would be ridiculous.
So this first one, this would be general power rule. Yeah. This would be chain rule. the derivative of sine? Curious, I think. Yeah. Two. I got two. 2 dy dx's. I can factor it out.
Good thing we have implicit differentiation right now. So implicit differentiation says, all right, why don't you go ahead and take the derivative of both sides. I want to see your work on this stuff. Show me your ddx's. Just don't forget both sides. Don't forget that. Now let's look at the right-hand side. That's going to be the easier of the two in this case. What's ddx of 4x to the fifth? How much is that?
20x.
So don't forget the stuff you already know how to do. Don't let that leave you. Now, this is where we get to be kind of careful, all right? If we have ddx of 3y squared plus sine y, you know how to take the derivative of this piece. You know how to take the derivative of this piece. Just be aware, you're dealing with, what are you dealing with, x's or y's here? Those are functions of x, which means that when you take a derivative, you will get a dy dx. Are you clear on that? Every time you touch a piece of your function that has a y in it,
Get dy dx.
with a derivative, you get a dy dx. Every time because of the chain rule. I'm going to stop showing you this right here, this whole chain rule idea. We're just going to do things like this. Check it out. 3y, what's the derivative of 3y squared?
6y.
6y, great.
Times
6y
dy
what?
dx.
Did you take a derivative of y? Did you?
Yeah.
Then do a dy dx. The reason is, again, you would have a chain rule. Chain rule would say, bring down the exponent, multiply it, take one away from it, that's the 6y, but then multiply by d dx of y, right? That's what we have over here, d dx of y,
I guess
that is your dy dx, and that's where that's coming from. How many
chain
people
rule
feel
can
you have a
require
6y dy dx? If no, you guys have questions on that right now. This part is coming from the same idea as this right here. It's the chain rule. You bring it down, you subtract, derivative of the inside, and that's what we're doing. Derivative of the inside in this case is d dx of y. That is dy dx. That's that piece. You need that piece, otherwise you won't be able to solve for your derivative. You with me? You gotta have that. So we need that. Plus, because we have a plus here. What's the derivative of sine? Cosine, okay. So we have cosine of y. Is that it? dy dx. You took a derivative of something that involved a y. That means dy dx. Again, if you want to see this, this would be the chain rule. You'd go cosine of y leave the inside alone, d dx of the inside, but that's just a y. That's dy dx. That's why we're getting that thing. That's where that's coming from. Do you see where it's coming from more now?
I'm just curious on how, like, because the derivatives will find the slope, how would you find the slope of that?
That's a good question. Let's solve
Find
for
the
this
point
and I'll
first.
ask you that. I actually have a
Give me
couple
the x and
examples
y.
later on that will illustrate
Okay.
what you do for that. So we're getting there. Right now I just want to get you handled on the derivative part itself, okay? Whew, oh man. What do you got to do now? Yeah, you got to solve it. So when you solve for a variable, you get all your variables to one side, right? Then you
Factor
try
out.
to combine like terms, and you try to factor until you get just one of them, and then you divide. And that's how you basically solve for a variable. Our variable here is dy dx. So get all your dy dx's to one side. Basic algebra here. Calculus is done. You're done. You've done the calculus correctly. Now it's algebra. So you see your dy dx here, your dy dx here. That means you're going to factor. So you're going to have to be good at factoring. If you factor that out, you get a 6y plus cosine y equals 20x to the 4th. So far, so good? Let's get rid of this nasty piece of junk. What are we going to do with that?
Divide by this.
Yeah, just divide it. This is being multiplied, correct? So if we divide both sides by that, so divide here, we're dividing by this expression, we get dy dx equals 20x to the 4th, cool, over this same expression, 6y cosine y. Is it really too hard? Not really. Not too bad. It'll get harder when we start doing some other rules in there, which we're about to start right now, and you just see that. But in general, the calculus is going to be very similar. Very similar stuff you've done, as long as you remember what's the important piece of information here? Yeah, you got to have the dy dx. That's the important piece of information.
What sort of practical application do we have if we're trying to find, like the first one we did was for a circle?
Sure.
Why would you want to find the top half derivative of the circle and the bottom half using it?
Well, I mean, those things exist in real life, right? So if we somehow need to find a tangent line to those, we can do it. So we can actually find tangent lines to these weird curves, which aren't even functions, not functions. We can still find derivatives of that. It's going to come back at you later in calculus, too, for when you have more than those variables, right? I mean, so you're going to have use for this later on, is what I'm trying to say. Did I answer your question?
Is it for something where you have you have multivariables and you're holding one constant and you're trying to solve?
You can. You can actually do partial derivatives, things like that. I don't know if that's, I forgot if that's the same thing as implicit, if you use that in that context, I'm not sure. But I do know that this is useful for finding those derivatives and those slopes of just any curve. In fact, if you really think about it, finding any curve that you want, you've been doing this the whole time. If I give you an explicit derivative, or explicit function, y equals 3x squared, I think I've used this a couple times. If you take the derivative of both sides, which is actually what you've been doing, check it out. You have d dx of y equals d of 3x squared minus 4. Now this, since it's a function in terms of x, it's 6x.
Oh, okay, that makes sense.
That's a function in terms of x, isn't it? Derivative gives you dy dx. You've actually been doing it the whole
By
time. You've been doing implicit.
the whole
It's just been
time.
nicely solved for you the whole entire time. That's kind of neat, right? So is there applications for implicit differentiation? Yes, because you've been doing it this entire time. Implicit just comes about because sometimes you can't solve for y, and that's why we have it. Still means the same thing. Still a derivative, just you cannot solve that for y. Good question. Are you ready to move on? Are there any other questions on this before we do? All right. Are you having fun yet? Isn't that kind of cool, right? I think it's cool.
For making headache.
No, that's later.
Here's the chest after yet.
No, that's this chapter. It's coming up. Don't worry.
Thanks.
Sure.
Oh, yeah.
See, it looks simple. Looks simple.
Why do I have two circles?
Huh? Implicit, explicit. What was this?
Implicit.
Definitely implicit because the y is not by itself. Can you take an implicit derivative of this? What is y? A function of x. What happens when you take a derivative of x, which is a function of x, times y, which is a
Product rule.
function of x? You see the product rule? You gotta have the product rule.
So we got first term times the second term, and add them together. First term times the derivative of the second term.
So what we can do, we can just go, oh, x is 1, y is dy dx. Yay, I'm done. Because then dy dx would equal 1, right? And that's not the case. In fact, if you were to solve this, what you're going to get is negative 1 over x squared. That's what that is. Because if you divide by x, you get 1 over x, derivative of that. That's actually negative 1 power. Bring that down, subtract 1 from it, you get negative 1 over x squared. Do you see that, what I'm talking about? That's got to be the same. Down, subtract. That's what that is. Because if you divide by x, you get 1 over x, derivative of that. That's actually negative 1 power, bring that down, subtract 1 from it, you get negative 1 over x squared. Do you see?
Wait. 1 over x, x negative 1, negative x. Ah, yeah. Right. A square root. Negative 1 over x squared. Okay, I see.
See that, what I'm talking about? That's got to be the same derivative. So here, when you have the product rule, yeah, you got to use it. That's a function of x times a function of x. So sure, we're going to take a derivative of both sides, and you let your d dx kind of do the work for you. You just follow that down. d dx of 1. What's d dx of 1?
0.
So don't forget about that. You always take the derivative of both sides. d dx of x times y, that's a function of x times a function of x. And that implies the product rule. So we go, okay, let's do derivative of the first times the second plus the first times the derivative of the second. Why don't you help me out with this, folks? You tell me, what's the derivative of x with respect to x?
1.
Good. And what else do I have?
1.
Do I need a dy dx here?
No.
Did I take the derivative of y?
No.
Then no, you don't need it. Plus, I know this x doesn't change. What's the derivative of y with respect to x? Yeah, that's kind of nice, right? Can you solve for dy dx?
But subtract y over
Are you okay on getting
divide
that?
by x.
Okay, solve for dy dx. What do we do?
Subtract y.
So x dy dx equals negative y. Good, divide by x, because that's being multiplied right now. If you divide by x, you get dy dx equals negative y over x. Now, I made you the guarantee that this is going to be negative 1 over x squared, and this is not negative 1 over x squared, this is negative y over x squared. Why is that? Well, because I solved this derivative by using implicit. If I had made this explicit, which you could do easily, that's 1 over x. True? Y equals 1 over x. If I plug in 1 over x, well, I get negative 1 over x over x. Over 1, flip it, reciprocate, you're going to get negative 1 over x squared, which is the same exact derivative. That's the same thing. Now, this is one of the rare cases where you could make your implicit function into explicit and do it the same way. I'm just giving you this as a kind of a for instance, that when you see this, you need the product rule. Like, can you see the product rule here? Okay. So do you need to do this? No, you don't. This is a valid answer when you're doing implicit. This is just fine. This is what I'm looking for, as a matter of fact. So don't forget about the product rule. You gotta see the product rule. Well, I don't know if this is fun or not. It's fun for me. I love this stuff. But do you understand it is really the main thing. Is what I care about. Whether you find it fun, honestly, I don't care. I would hope you do. But I care that you get it. Do you get it?
After some practice.
Yeah.
Oh, yeah, boy, yeah. Yeah. I don't expect you to get this out on the first go. I mean, if you do, great, and you're able to do all of them, sure. But yeah, there's going to be some tough ones in there that you are going to have to practice. I also need to show you this. Could you take the derivative of that?
Let's see. This looks like a circle. Well, actually, I don't know about, maybe not. 2y times dy dx. Is that it?
Hey, why don't you practice that right now? Go ahead and find the derivative. Find dy dx. Do you need a product rule for this problem?
No.
No.
Thankfully. Thankfully, no. Okay, so that becomes 6x, that becomes 2y. Did you get the dy dx? If you lose the dy dx, you get lost on the problem, right? Because then you don't have a derivative to solve for, and you're like, what am I supposed to do now? That doesn't make any sense at all. So you have to have those dy dx's. That stands for your derivative. Did you make it that far? Everybody, have a show of hands. Some people made it that far. Good, okay. Now we solve for it. Solving for it says, well, actually, it'd probably be nice if I added this to both sides and divided by 2y, but I'm guessing most of you subtracted 6x and divided by negative 2y. You still get the same answer, but you have to divide by negative. Guess that doesn't matter. Negative 6x, if we divide by negative 2y, you're going to get positive. Did you get positive 3x over y?
Yeah.
Yes.
Everybody. Great. Now, unfortunately, this is not the question I'm asking you for.
It's too easy.
That's the question I'm asking you for. Okay.
What?
A second derivative. Now,
Well, that's not that bad, is it? You just use a quotient rule with this. We already found the first. Yeah, maybe this isn't the way to go. Okay. Well, I'll keep this for now. Actually. Okay, so this would be on the right side, wouldn't it? Whoa. dy dx. Yeah, never mind. I'll have to look at an example for this one.
can you take a second derivative of this thing? Of course you can. But in order to take a second derivative, yes, you have to solve for the first derivative. So, well, to do it correctly, you have to solve for the first derivative. So we solve for the first derivative. The second derivative just says, hey, check this out, it's kind of neat. Why don't you just take a derivative of both sides? So go ahead. And
Oh, okay. That's it. Bring that back. d squared y dx. Ah, yeah, I see. Should be it, right?
And do that, can we take a derivative of both sides? Watch how to accomplish this. If we derive both sides, we get d dx dy dx equals d dx dx over y. Can we start with the easy side first? Firstly, easy side first. A derivative of a derivative gives you a second derivative, and you're going to see the notation come into play. Do you see this? Look at how many d's do you have? 2d. So d squared y. Remember where that comes from? Okay, cool. Over, the only one that doesn't work is this d. You don't get d squared x squared. It really should, if you wanted to do that, it should be like that. We just never show that. This becomes d x squared, and that's where you get the notation for a second derivative. Are you seeing where that notation is kind of coming from? It's cool, I guess. If you're me, it's cool. I don't get out much. What are you going to have to do for this? Use the quotient rule. Go ahead, set up the quotient rule. You know the quotient rule now. Go ahead and do it. Just everywhere, it's easy. It's an easy derivative.
Factor out
Just
of 3,
everywhere you
huh?
see a derivative of y, you have to put dy dx.
I'm not, though.
Don't forget about that. And then you're fine. I make it sound so easy when I'm doing it. I said, and then you're fine. Oh, before that.
Yeah.
Use the quotient rule, sure, set that up. Everywhere where you take a derivative of y, you need a dy dx. What I tell you to do, low d high minus high d low?
How do you-
Okay,
Towards
so
bottom
low d high minus high d low. Again, not to be confused with CeeLo. CeeLo is the guy with glasses on The Voice. Very cool show. Love that show. All over bottom square. I guess I could use parentheses there as well. Did you set up the quotient rule correctly? So that stuff's not going to change. I've taught you. I told you there's only 3 rules. I've taught you all 3 rules. Now it's just applying them. So do I take the derivative of that y?
No.
So this is going to be y times. Do I need a dy dx? For this one. For this one.
No.
No, because I'm not taking derivative of y. That's going to be 3 minus 3x times, what's this going to become? There it is. Perfect, y squared. That gives you, if we clean this up just a little bit, 3y minus 3x Now wait a second. This is weird, because I have a derivative, and I have a derivative.
I'm guessing you just plug in the original derivative dy dx into that.
That's strange. Do I want to solve for that? No. No. The reason why you don't want to solve for that, look at the board. Have you already solved for
Yeah.
that? How much is that equal to? Right there. Just plug it in.
Nice.
So you're going to find dy dx's, but if you're taking the second derivative, you will have already solved for dy dx. That's cool. Now, chances are, for you guys, you might not always get it like this, all right? If the back of the book looks different than this, what they probably did, because you have a complex fraction, is they got rid of that y. If you wanted to get rid of it easily here, instead of finding a common denominator, just multiply everything by y, and that'd get rid of it. We did because you have a complex fractions. They got for you guys, you might not always get it like this. All right, if the back of the book looks different than this, what they probably did because you have a complex fractions, they got rid of that y. If you wanted to get rid of it easily here, instead of finding a common denominator, just multiply everything by y, and that'd get rid of it. So multiply y, multiply y, multiply y. You're going to get 3y squared minus 9x squared over y cubed. Do you see what I'm talking about? That should be the same thing as finding a common denominator. Get that.
Be drawn a problem if we leave that y in there. Would you mark us wrong on the test for that?
You know, I'm not sure. I'll have to think on that. I would like it as simple as possible. Now, sometimes you're going to get some nasty things, and it would take you more time than that. So either I won't give you stuff that's going to be really nasty, I'll give you stuff like this that you can simplify pretty easily, or I would say just leave it, okay? Now, I'm going to come back and answer your question here. The question is, what in the world does this stuff mean? What are we doing here? Are we still finding derivatives?
Yeah.
And what does a derivative mean? Well, you have those words backwards, but I'll kind of show what you mean. The slope of a point? No, not really. Slope of a curve at a point? Yes. So if I say, here's y squared minus x plus 1 equals 0, definitely an implicit equation. Can you find the slopes of that curve at two different points?
Wait a minute. Slope of that curve at two different points. This looks really close to slope-intercept form, that's why I'm like, Alright, I'm just gonna take the derivative, screw it. Alright, slope of a curve at two different points. Alright, well here's my points. For no reason. 1, 1, 1, 2. So if I curve it up at 1, 1 would be half. So if I curve it at 1, 2, be a fourth.
Find slopes at 2, negative 1.
Oh, okay.
And 2, 1. Notice something interesting that happens.
2, 1. There's no x. Yeah, there'd be no x.
Look at this. Because I have something that's not actually a function, it's implicit, I'm plugging in the same x value, and I'm actually getting out 2 y values. Do you see that? Also,
Oh.
notice that I am implicit, which means I have to give you both x and y for you to accomplish this problem, because your derivative is going to be in terms of both x and y. Do you see it? So that's how you use this. Now, let's go ahead and end this problem real quick.
Did I do it wrong?
This is a pretty easy derivative. If I derive both sides, I'm going to get d dx of the left side equals d dx of the right side. Start with the easy side. What's the derivative of 0, please? 0. Good. Derivative of y squared.
2y times dy dx.
Perfect. Minus how much?
1.
1 plus how much?
0.
Good. Derivative here is 2y dy dx. Derivative here is 1. Derivative here, nothing. Can you solve that? If you add 1, you're going to get 2y dy dx equals 1. If you divide by 2...
Oh, I see how you got plugged in one thing, got 2 different values, yeah.
y, you get dy
Because of the
dx
square root
equals 1 over
functional
2y.
function.
What did you just solve for? What is this thing? What is it? That's m. Yeah, that's it. That's slope. That's what that is. So this is a slope function. Now, it says find the slope at 2, negative 1, and 2, 1. Is there a place to plug in the x? Not even a place to plug it in. I don't even care about that. Plug in whatever values you can. If they had both x's and y's, you'd plug in both x's and y's. If it has only x's, plug in x's. If it has y's, plug in y's. So what we're trying to find is a slope at 2, negative 1. 2. For 2, negative 1, I would have 1 over 2 times negative 1. For 2, 1, I'd have 1 over 2 times 1. This one gives me negative 1/2. This gives me positive 1/2. Interestingly, here's what we've done. We found the slope of that thing at the 2 points. So 2 different slopes because we're going to have 2 different outputs for that same input. Interesting question. How many people understood what we talked about so far today? Okay. I'm going to start you off next time with quite a brain buster. After that, we're done. There's really only one more problem that we have to do. So I want to show you a couple things about that. Now,
See what that looks like. Y squared minus x plus 1 equals 0. Oh. Yeah, definitely not a function. function that does not pass the vertical line test is called a relation. Really? So this is a relation.
Now, we'll start on that next time. All right, so today, like I said, we're going to continue talking about implicit differentiation. That's what we're doing. We're still finding a derivative, but we're realizing that we can take this implicitly. So if we can't solve our function for y like that, which this is actually an equation, not a function, but if we can't solve it for y, that's called implicit. So this is definitely an implicit equation. We're going to be able to find the derivative, which still means slope, of that thing. So here's the question. The question is not just this, but can you, with this equation, find the tangent line at a certain point?
Yep.
Find the equation
Oh, equation.
of the tangent line at the point 2, 1.
Alright, I'll do that in a second. Okay. Let's see. Four x to the fourth plus, you know what, I'm not gonna write it out. I'm gonna just find the derivative right away. D dx, 4x to the fourth plus d dx 8x squared y squared minus d dx 25 x squared y plus d dx 4y to the fourth equals d dx 0. So we got 16x to the third plus a product rule. Great. Okay. I'll do this off to the side. Minus. Are you kidding me? Another product rule. Plus. Okay, I can do this. Is this another product rule? Yep, maybe I could use general power rule for this one instead. So 16y to the third times dy dx. I hope that works. Equals 0. So for the first one, you have 8x squared ddx, ddx, 8x squared times y squared plus 8x squared ddx 8x what? No, y squared. Yeah. (16x) times y squared plus 8x squared times 2y times dy dx. Bruh. Okay, we can, yeah, like that. (16xy squared plus 8(16) x squared y, because it can't be easy. Times dy dx. For this one, (25x squared ddx 25x squared y minus 25x squared d dx y. (50x y 50x times dy dx. Okay. And this whole thing, 16x cubed plus 16x y squared plus 16x squared y times dy dx. Minus 50xy minus 50x times dy dx. And there's the other part too, so I gotta shrink it. Plus 16y cubed times dy dx equals 0. Yeah, this is certainly one of the problems ever. 16x cubed plus 16x y squared plus 16x squared y dy dx minus 50xy minus 50x times dy dx plus 16y cubed dy dx equals 0. So I'm thinking move every term of dy dx to the left, and then every term that doesn't have it to the right. 16x squared y dy dx minus 50x dy dx plus 16y cubed dy dx equals negative 16x cubed. I'm gonna shrink this. Minus 16xy squared plus 50xy, and that's it. Now factor this out. Dy dx 16x squared y minus 50x plus 16y cubed equals negative 16x cubed minus 16xy squared plus 50xy. Okay. Divide by this whole thing. (16x squared y minus 50x plus 16y cubed dy dx equals negative 16x cubed minus 16xy squared plus 50xy all over 16x squared y minus 50x plus 16y cubed. And that's the first step. Alright. Now we're finding the equation of the line, of the tangent line at 2, 1. So first we gotta find the slope. So we already have our point, luckily. So 2, negative 16, 2, I'll plug in all the x's, 16, 2 plus 50, 2, 16, 2 squared is 50, 2 plus 16. There, and then the y is 1. 1, 1, 1, 1. Now solve. So, let me make sure 2 cubed is 8. I'm not trying to mess anything up. So 8 times negative 16 is 32. 1 plus 100 times 1. It would really suck if I messed something up here. If I got everything else right. 4, 16, minus 100 plus 16. Times 8, 128 minus 32 plus 100. Sixteen times 4, 64. Minus 100 plus 16. Negative 128 minus 32 plus 100. I'm being very safe. Negative 60. I'm not trusting my brain right now. Only the calculator. 64 minus 100 plus 16. Okay. This is looking good. It's a clean answer. 3. Slope of 3. And the original point was 2, 1. Y minus 1 equals 3 times x minus 2. Y minus 1 equals 3x minus 6. Y equals 3x minus 5. And that's the equation of the tangent line at 2, 1 for the function, whatever that thing is. If it's a function. Probably is.
By the way, with something like this, could I just say at x equals 3 or x equals 2? Could I have done that here?
Yeah, then you plug in to the original.
Not really, if you can't solve for y.
You know what? Yeah, that's a good point.
Because even if I plugged in the 2, you'd have a bear of a time finding out what the y would be. Does that make sense? So really with these implicit ones, they're going to give you the full point. And we're going to see that for the derivative as well. So let's go ahead and let's find the equation of a tangent line at that point. What do you need to do to find the equation of a tangent line? Good, because for any line you need 2 things. What are the 2 things you need to find the equation of a line? Slope and a point. We have a point. We now just need a slope. A slope is a derivative. So we're going to go through this. I want your help with it, but I'm going to do it on the board for the sake of time, just so you see it one more time. The implicit stuff, I've already taught you how to do all that. So right now it's really just practice for you. And one thing you're going to see up here that's very important as far as our signs go. So with the implicit differentiation, it says you take a derivative, d dx, of both sides, and we treat y as a function of x. What that means is y is a function in terms of x that we just don't happen to know. So if we're taking this with respect to the variable x, and y is a function of x, we're going to get a dy dx every time we touch a y with the derivative. Does that make sense to you? So we're going to be getting that. So in our case, here's all the work shown for you. We're going to take a derivative of both sides. Even though that's a 0, I'm still going to show the derivative just for the sake of,
Because that's technically what you're
being
doing.
correct. And so you don't forget that even if it's a constant or something, you still have to take a derivative of that. So we're taking a derivative of both sides. Of course, a derivative of 0 is still 0, so we're good on that. Now let's look real careful at these pieces over here. Is this a hard derivative to take?
No.
The 4x to the 4th. What's a derivative of 4x to the 4th?
16x to the third.
Okay, so let's do that. So we got that derivative. How about this one? Is this
Product
one
rule.
different for us?
Yeah, product rule.
That's a product rule. Why is it a product rule?
You have
Two
one
different
certain
functions.
in terms of x multiplied by another function.
Sure. So this is a function in terms of x right there. That is an x. Now, we said y is a function of x as well. So every time you get that, you do need product rule. Or if you had a fraction, you would need the quotient rule. So you have to have that. So in our case right here, we do have a plus. So write a plus. Now, there's a couple things you can do with that 8. You can treat it as 8x squared, that's one term, or you could pull the 8, since that's a constant, you could pull that out front. That really wouldn't matter. Now, you're probably going to be distributing that anyway, so leave it in there with the 8x squared, that's fine. But you could pull that out. Do you see what I'm talking about? That's possible. So here, I'll just treat it as 8x squared. That seems to work okay for me.
Because you're going to distribute it anyway.
So derivative of the first times the second plus the first times the derivative of the second. By the way, note that even when I'm taking a derivative of y, I still have a dx. Do you guys see that I still have the dx? It can't go switching variables. So if you start with the ddx, it's got to be that all the way through. All right, so that's there no matter what. Still okay so far? So we've just done the product rule. And you know what I'm going to do, since this piece was right here, just for, you're going to see this, why I do this in the next one, just for the sake of being, have a continuity in the way I'm going to do things here, I'm going to put a big bracket around that. That's saying this came from that one term, and that's a great thing to do. The reason why it's a great thing to do, you're going to see this in the next piece. If you do this here, it really doesn't matter, because that positive isn't going to change any signs. You see what I'm saying? However, what's going to happen if I don't do that with this one? I'm going to really blow my problem up.
Hope I didn't do that. No, I definitely didn't. I was really careful with that actually.
Okay, that's going to explode my problem because the sign's going to be incorrect. You're going to see that right here. Let's look at the next term. I have a minus sign, so I'll write a minus. 25x squared y. That's still a product rule. Product rule says maybe take the 25 with the x squared. ddx of x squared. That's the derivative of the first. Sorry. Derivative of the first times the second plus the first times the derivative of the second and I want you to see something. Now, when this said take the derivative of this piece, it means I'm going to subtract the derivative of that piece. The derivative of this piece isn't just this thing, is it? It's the whole thing. So if you don't have a big bracket right here, that sign's incorrect, right? If you do have a big bracket right there, that's saying that what's going to happen is this negative is going to change those signs in there, and that would be the correct way to do it. How many people see that? Okay, that's an important thing. That's actually why we did this example, just so you can see that. Otherwise, you're going to be off by a sign somewhere. And then, that's a good place for a plus. Plus, let's do this piece. What's that piece? Okay, I'll give you a 16y cubed. Do we need a dy dx on that? Every time you touch a y with a derivative, you have to have a dy dx on account of, what rule was that did that? General power rule, or in general, the chain rule. That's right. The chain rule says that.
Derivative of the inside.
Equals 0. Now that's a long problem. Did you think you'd ever get a problem that long? That's ridiculous, isn't it? It's like a whole piece of paper right there. Are you okay on what we've done so far? So we've done real easy one, no problem. Product rule, dy dx because we're touching a y with the derivative, and then we have 0. Yes, no? Now we start following the ddx. This is why I've made you write the ddx on your problems, because it will tell you what to do next. It says this piece is done. You're just going to have the 16x cubed plus. Now this piece in here, this just says do this ddx. So everyone, 8x
16x.
squared, what's the derivative of that? And then it's y squared. Notice there's no dy dx because I don't need one here. This is just the derivative of x. Plus, I'm getting rid of my bracket because I know none of those signs are going to change. Everything was positive, that's okay. So this plus doesn't change anything here. That's where those brackets are disappearing to. Then plus, I have the 8x squared. Tell me the derivative of y squared, please.
2y
When I'm
times
taking a
2y
derivative
dx.
with respect to x. What is that?
2y dy of dx.
Good, 2y, but not just 2y, right? If I just do 2y, you know what happens? If I do this,
What's up?
and I forget a dy dx, what's
problem's
going
what's
to
up?
happen is you're going to be adding or subtracting this term over instead of dividing by that term because you factored out a dy dx. Do you see the difference
Yep.
there? That's going to really make that ending fraction, which we're probably going to get, look really weird. So it's really important to get that dy dx because that gives you another term that you're going to factor dy dx out of. Minus. Okay, let's see about here. The derivative of this guy.
58.
And then I have a y. Now, when I've already gotten rid of this bracket, are you guys okay on doing a couple pieces at once? When we get rid of this bracket, what's going to happen to that? So this isn't math magic, right? I'm not Harry Potter. Gone. No more pluses. Ha 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 ha. No, what's happening is I'm getting rid of the bracket by distributing to these pieces. Notice the bracket ends here. That minus won't affect this plus, but it will affect this plus. So 50xy plus, or sorry, minus 25x squared, and the derivative of y, everybody. Yeah, very good. Then I'll have a plus 16y cubed dy dx equals 0. Give me a little quick head nod if you're okay on this so far. Yeah? Okay? Oh my gosh. Wow, what now? What now? Done! Yay! Super duper! No, not even close. Well,
Move all
okay,
your
if it's
terms
done,
of dy dx
give me
to
the
the
slope
left.
then. Because we want the equation with
All the
tangent
ones
line.
without to the
This is our
right.
goal.
Factor.
Right? This is not our goal.
Get all the dy dx's on one side and everything else on the other side.
Brilliant, yeah. If we get all our dy dx terms on one side, then we can factor that. If we get everything else on the other side, that's great because ultimately we'll be able to divide. Follow? So let's get all of our dy dx's. We'll leave those on the same side, and then we're going to add or subtract our terms depending on their sign to get them over. So we will be subtracting our 16x cubed, our 16xy squared. We'll leave this one alone. So we want to leave this guy right here. We'll be getting rid of this one. We want to leave this one with the sign and leave that one. By the way, are you okay that I'm going to make this 16x squared y? You're all right with that too? So notice that this is 16x squared y dy dx. Make it a little bit nicer looking. So 16x squared y dy dx. That's that one. So I got that. Minus 25x squared dy dx. I got that one. Plus 16y cubed dy dx. I got that one. Equals. Well, we have to add this and subtract these two. So you can write this in whatever order you want. It really doesn't matter. We're going to have these three terms on the opposite side. The signs will look different because we're adding or subtracting them. So if I add this over, I get 50xy. If I subtract these two, I'm going to get minus 16x cubed minus 16 xy squared. Are you still okay so far? Okay, great. dy dx's are all on one side. Everything else is on the other side. What now?
Factor out dy dx.
Let's factor. So if I factor dy dx, notice how when we did this, every term, as it should, has a dy dx in it on the left-hand side. We'll factor that out, means divide everything out. We'll have a big bracket. And now we have dy dx times this enormous factor. How do you get rid of an enormous factor being multiplied by something? Divide. You can divide by this entire expression right here. That entire factor is going to go under this expression on the right-hand side. Do not mess that up. So dy dx is this thing all over that thing.
Let's see if that's what I got. 50xy minus 16x cubed minus 16xy squared over 16x squared y minus
Okay, quick show of hands. How many people were able to follow?
25. Are you kidding? Plus 16y cubed. Is that the only thing I got wrong? Let's see, where's this from? Oh, this is the point. It's 25. See, minus 50x. Would have been from that. Minus 50x times dy dx. So I got 16xy squared. Wait, no. Take the derivative of 25x squared. 50x times y minus 25x squared. I took the derivative of that. Yeah. That messes up part of my problem. X squared. So close to it, dang. 25x squared. 25x squared. Alright, does that look... Okay, I gotta redo this now. $25 squared for... Wait. That's so lucky. it ends up being the same thing anyway, because I did 50 times 2 before, and now I'm only doing 25 times 4. That's so lucky, what? Okay. I'll take it.
All that, feel okay with it? By the way, did I do it right?
Man, that was lucky.
Oh, good, okay. Because I haven't had to do anything all day, so this is my first actual teaching class, so my brain's still a little rusty. So hopefully I did all that right. Or maybe I'm extra good today, because I had to waste my time on other stuff. Ooh, you're getting an extra good lesson today. I like that look. Okay, so we have this. By the way, you should try to simplify this, if you can factor and simplify. Now, you're seeing an x here, which you can factor out, but there is not an x common to all three of those terms, so it really wouldn't help you in this case. Also, you look for any constants to factor out. You really don't have, you have a 2 here, but not a 2 there. So there's nothing really much that we can do. Do you see what I'm talking about? What did we just find?
So the
Slope.
one.
The equation for the slope. The formula for the slope. Now, we said find the equation of the tangent line at that point. Do you have x's and y's? Did I give you x and y?
Nope.
Plug it in. This is the slope. Do that. That's the slope. It says plug in the numbers and find the slope. And I have no idea what it's going to be, so you have to do this correctly. I think it's going to be nasty, though.
Nope.
Looks horrible. Horrible. I give up. I'm done. Just wait for you. I got to 100. That's it. Oh God. Stop. 16.
Or 66.
I don't know what I got yet. I got 3. I don't have a calculator. Shame on you.
I got 3 too.
Did you do it without a calculator?
Yeah.
Awesome. Awesome.
You said it was gonna be next.
No, really nice. I'm a nice guy today.
It's amazing how that big old problem.
Isn't that weird? Crazy. You're like, I expect negative 1,257 over like a third. I don't know.
All that
Well,
just to get a
yeah,
slope.
but all this, and you think this is a hard question, it's really not. This is the easy part. This is the hard part, is find the slope. Because once you, I mean, if you talk about a slope has to be a number, right? A slope has, a line has to be a constant number. So plugging in things, you should get a constant number. Now this is very easy. Y minus y1 equals m, x minus x1. You get y minus 1 equals 3x minus 6, add the 1.
Oh, that will be
That's your answer. Yeah. This doesn't come about at all, right? Oh, by the way, don't plug this into not the right way to go. Use that to find your slope. Does that make sense to you? So this is about the hardest derivative I've ever really seen for implicit, unless I threw a quotient rule at you within that. Which
Some of the ones in the homework were harder.
some of them are harder, but this is the, if you can do that, you're fine. Okay, if you can do that and one that involves a quotient rule, you're fine. I think I did give you one of those earlier in our lesson, so refresh your memory on that. It should have been the second derivative of something. I think we did that. I showed you how to plug in that dy dx. So this ends our implicit differentiation. Are you okay with the idea of implicit differentiation?
So we shouldn't be too worried if some of the problems in that homework are absolutely murdered.
No, don't be murder. I mean, some of them, I told you before that some of them are very, very hard.
Some of them nonchalant. Some of them are just really,
Some of them will be
murdered.
Some will be murder.
I guess you're okay.
Am I going to give you a problem that takes you 45 minutes to do on a test? Maybe. Maybe. I probably won't do that to you.
I feel a little bit better.
Unless I just give you a test that has one problem on it.
Or you decide you really want to fill everybody in the class.
And say, this is your final, congratulations. And sit back and drink my coffee. But I probably probably won't do that.
But you won't roll it out either.
Probably. Greater than 50% chance that I won't do that. No. Anyway, do you have an idea of implicit differentiation? Now, what's kind of cool is that we can use this idea of implicit differentiation to take a derivative of whatever we want with respect to whatever variable we want. I know it's a weird idea, but here's how we can use it. I'm going to introduce the idea of something called a related rate. These are all word problems. I know some of you have it's the bane of your existence, are word problems. If you think through, I'll give you some steps on how to do these, and of course, I can't give you an example of every type of word problem there is. Lots of word problems. But what I will do is give you a technique on how to do these related rate problems. Are you ready for it? So we're talking about 2.8.
Alright, nice.
Related rates.
Hey, this is the last video in chapter 2. And then for 3, there's basically 1, 2, 3, 4, 5 videos because 3 of them are like really short. And after I get this done, then I really will be halfway through. Nice.